Good afternoon and welcome to the Museum of Science. We're delighted that you were able to join us today. Professor Amir Aczel is a research fellow at the Center for Philosophy and History of Science at Boston University. An award-winning author, he has penned 16 books on science and mathematics, including the international bestseller, Fermat's Last Theorem. His new book, Uranium Wars, weaves a suspenseful story about the brilliant men and women who raced to harness the mysteries of radioactivity. Please welcome Amir Aczel.
Thanks. It's a pleasure to be here at the Museum of Science again. The story of uranium starts already in the 1800s. In 1895, Röntgen discovered X-rays, and so people were very excited about this idea of action at a distance, this radiation, something we don't see, that affects something far away. In Röntgen's experiments in Germany, he, of course, did something he didn't understand, and he saw a glow from a piece of paper a little farther away, which had some coating on it, and when he turned it off, he realized the glow stopped. So there was something that acts at a distance, and that really fascinated physicists, and it was the most exciting things in physics that had happened at that moment. And now physicists were looking for ways to discover whether there are any naturally occurring substances that can create the same kind of thing. And they discovered uranium. Now, uranium actually was known to the ancient Romans. And uranium is a very strange element. It's produced in supernova explosions in outer space. Now, many of the elements in our bodies and in the environment, the heavier ones, are all derived from supernova explosions. The lighter ones occur just as normal stars die in other ways. So this is a very sort of out-of-this-world type of an element, and it's the heaviest one in the natural environment. It has 92 protons and 146 neutrons. So this is a proton. It's not, but it will stand for a proton for us. And this will be a neutron. So as you can see, they're the same size, but they're different from one another in that the proton has a charge. It has a positive charge, and the neutron is neutral, as its name says. Now, today we know a lot more. We know that each one of these is made out of 3 quarks. So I hope you can see this. There are those 3 quarks that live inside each one of these, but this wasn't known until the 70s. Professor Friedman of MIT, whom I know, actually was the one who saw them. Now, they were proposed to exist by Maury Gell-Mann, who got a Nobel Prize, and I'm sorry? Oh, yeah. And Professor Friedman devised an experiment to see them so he could see inside a proton or a neutron. It was very difficult because these guys don't live outside at all. They can't. And today we know that regardless of the amount of energy that you expend, you cannot separate a quark by itself. It's absolutely impossible. Now, it's something you say, well, why not? Get more energy. No, quarks can't live alone. So when you break the proton or a neutron, the quarks immediately find partners. They're anti-quarks that link to them. So you have 2 together, which is called a meson. Or they live inside here. And inside the LHC, for example, the Large Hadron Collider in Switzerland, which I just visited a few months ago, the energy there will be huge, 14 tera-electron volt. But when that happens and they crash 2 protons together, they crash them together, so you destroy them completely with immense energy. They travel at 99.999991% of the speed of light. It's, if one of these protons races a ray of light to the nearest star, which is Alpha Centauri in the southern hemisphere, 4.25 light years away from us, the proton arrives a third of a second later after the light ray. So you can imagine how fast they're moving. So they break into each other. They crash with immense energy. And yet what happens is that these guys come out as jets. And the jet is like a fluid that comes out. They're all linked together. They cannot be separated. Another professor at MIT, Frank Wilczek, proved why they can't be alone. So there's a whole theory of that. But none of this was known in the 1800s. And as we move into the 20th century, Marie Curie, who worked in Paris, was the first major scientist to work with radiation. And as we know, made lots of discoveries. She discovered radium and polonium, and really understood how radiation works. Unfortunately, she died of cancer. Her hands were pretty much burnt because she worked with radioactive elements constantly and took no precautions. Other scientists were more careful and actually did live to old age because they were very careful with radiation. I started saying that the Romans knew about uranium, and I didn't finish that story. The Romans used it to dye as tinting element for Roman glass and for potware. And this was used actually very late in the 1950s. The Chinese were still painting dinnerware with uranium minerals. I was a professor at Bentley College until a few years ago, and the head of the natural sciences department once invited me and said, look, there's this beautiful dinnerware from China, and I held it, and then he went back and brought a Geiger counter, and he said, closer. It was pretty scary. So, those of us who are my age or older still remember the watches that, of course, had radium, which Marie Curie discovered. Radium is a lot more radioactive than uranium, and it's a product of it. And radon gas, of course, that gets into our homes when we're not careful, is also a product of uranium. So these products of uranium are much more radioactive. Uranium itself is weakly radioactive, but it's the radium in it, like in that plate, that really causes most of the radiation. So Marie Curie, who died relatively young and did all these experiments, got 2 Nobel Prizes, and her husband Pierre got 1. And their daughter grew up in the lab, and she was called the little princess because in this lab she could run around and do whatever she wanted. So as she grew up, she became the next scientist in this family, and she got a Nobel Prize as well. So she tried to continue the work of her parents on radiation, and there evolved this kind of a race among 3 groups to try to understand what it is about uranium that makes it tick, so to speak, that Geiger counter tick, and what can be done with it, what can we learn from it, and how can we use it for various things. So her name was Irene Curie, and she and her husband Frédéric Joliot continued work at the same lab in Paris. Now I should say that when Marie Curie started her work, her mother, when she started her work, uranium was brought to her lab. A ton of uranium was brought from a mine in Germany called Joachimsthal on a cart, a whole ton of uranium in a cart with branches and rocks to the center of Paris and downloaded into her lab. And I often wondered how the French cleaned that radioactive waste from the place that has all these cafes around it. And nice area in the heart of Paris, in the 5th arrondissement, the area of the university, by the Luxembourg Park, for those of you who know Paris. So it's the nicest part of Paris, to my mind, and a ton of uranium sitting there at some point. So once the early work was finished, Irene Curie continued, and she competed against 2 other teams in terms of trying to understand how uranium works. One team was in Rome, and that was Enrico Fermi's team. Enrico Fermi was a major scientist who did lots of innovations with work on radiation and other things in physics. And the other team was in Berlin, and that team was headed by Otto Hahn, a very Germanic kind of a German person who was very precise and worked in the lab. And by the way, he was very careful, and radiation didn't affect him. He died at 89. And Lisa Meitner, who was an Austrian Jewish woman who had to work very, very hard to become a physicist, because in those days women were very strongly discouraged from getting into the academic world. In fact, the boys in Austria of those days were encouraged to go to gymnasium, which was a rigorous high school, which would prepare them for university, while the girls were not allowed into a gymnasium. Now, she wanted to be a scientist. And so what she did is she had to go to the girls' school, and when she insisted against her parents' better judgment that she wanted to become a scientist, they had to hire her a tutor to bring her up to speed as to what the boys were learning normally in school. But she was extremely ambitious. She was Jewish also, so she had suffered also from anti-Semitism and discrimination against women. But this was a woman who was determined to succeed in life. She worked very hard, and she got a doctorate at the University of Vienna, and then she moved to Berlin. Now, some of you may know of Max Planck, who was a famous, the first discoverer of the quantum idea. He was an old-style physicist who never really understood what he had discovered himself. Because he discovered the quantum, and it didn't make sense to him. But he was a major physicist, and when I went to Berlin to research another book, there's the academy, there's still his formula is on the wall there. He's a very major physicist. And Lisa Meitner, already with a PhD, came to talk to him. She said, I would like to audit your class, sit in on your class. And they said, why? So that discrimination was so endemic to these institutions. At any rate, she worked very hard. And she got to work she got a position at the Institute of Physics in Berlin, the Kaiser Wilhelm Institute, but she was relegated to the basement in the building. So the men were allowed upstairs in rooms like these, where ideas were discussed and lab work was done and so on. And she had to work in a carpenter's bench in the basement. I'm not joking. That was what her life was. But she was so gifted and ambitious, as I said, that eventually she became a major scientist. So she and Hahn were the competing team against Fermi in Rome and Marie and Pierre Curie's daughter, Irene, and her husband in Paris. So what these three teams were doing is what I'll try to demonstrate now. So the white balls are the protons, and the black ones are the neutrons. And I have a few more. Now, uranium is very heavy. I would have needed another bag like this to create a real uranium nucleus. But it's very tightly packed. So they're packed together very tightly like this. Can't close it, and which is why it's radioactive. Can't hold together, and it comes out. So, and this is an electron. Now, those of you who know physics, you know the electron is 1,800 times smaller than a proton or a neutron. So, but then you won't see it. So, at any rate, it's smaller, and the electrons go around the nucleus and in shells. And if you know about quantum mechanics, you don't know where it is. It's here or there or everywhere at the same time. And there's only probabilities in terms of understanding where an electron would be. And here's a nucleus. And what these three teams were doing is very strange. If you think about excuse me, what scientists do, what physicists do, is they're like children. They try to break things. So when I was a kid, I got a transistor radio, and I smashed it. I wanted to see what's inside it. Apparently, that's what particle physicists do at CERN, for example. They smash particles to see what's inside it. So these scientists, what they were trying to do is just that, smash neutrons into nuclei. And you think, what a crazy thing to do. And labs paid their way to do exactly that. And what they were convinced that they were doing is creating, sort of improving on God. God, so if you believe in God or the creator, whatever you want, on Earth we have this largest element, uranium. Let's see if we can make it bigger. So the three teams were conducting experiments for years of bombarding these nuclei with neutrons, trying to make it stick, to make an element that's larger. And they called these hypothetical elements transuranium elements. So the neutron was discovered in 1932 by James Chadwick in Britain. And Enrico Fermi discovered an amazing way of doing this experiment. At first, what he did was to use alpha radiation. So radiation goes in letters alpha, beta, gamma. Alpha is I only have two hands, so this is an alpha ray. A ray or particle, same thing, because of quantum mechanics. A particle is a wave, and a wave is a particle. And even you are a person, but also a wave. But your wave function is very small, so we can't really. So all things are really waves too. So not only you, everybody. So well, this goes to teleportation, for example. If you try to teleport, they can teleport the quantum state of a particle using particle wave duality, but you can't do it with a person because the wavelength is too small. At any rate, here is an alpha particle. So it's also a ray. It's a wave, right? It's a wave, but it's also a particle. So you can tell me right away what it is. Most of you maybe know there's two protons and two neutrons together. It's a helium nucleus. And what they were doing, this comes naturally from radiation. This is alpha radiation. Beta radiation is this. It's an electron. And also anti-neutrino, but that doesn't matter. And the gamma radiation is just energy. It's like a high-energy photon, like ray of light, but with much higher energy. So they were bombarding uranium nuclei, and of course it's much bigger than this, with this foursome. But it wasn't working. It wasn't working at all. And the reason it wasn't working is the same reason that when I go to get my laundry, I only find a single sock. I don't get two socks. I don't know about your experience. I suspect you have the same experience. And what's the reason for that? The socks get static electricity, and when it's the same charge, they repel each other. So if you find one, the other one is stuck somewhere. So this is what happens, the same thing. What's a charge on this, on the helium nucleus, on this alpha ray? +2, right? Because these two are neutral, and these two are positive, right? These two are positive, these are neutral. So it's +2. The nucleus is what? Has a positive charge too. So it's like the two socks. This sock, so you bombard it, but it goes away, right? So it doesn't work. So Enrico Fermi discovered something amazing. If you bombard beryllium with this foursome, every 100,000 of them will create a single neutron. So it's very wasteful in a sense. For every 100,000 alpha rays that hit beryllium nuclei, you get one neutron coming out. So it seems like a very wasteful kind of process. You do a lot of radiation to get 1 per 100,000. But he was so smart that he figured out this is a golden bullet because it's neutral, has no charge, no more socks. This goes and it's not diverted. It will hit. So once he discovered that, the three teams started doing this experiment again and again and again and again. So they're bombarding this. And they're waiting to find a larger element than uranium. And Enrico Fermi got a Nobel Prize for discovering it, which he didn't. So he deserved the Nobel Prize because he did a lot of other things. But he didn't discover transuranium element. What he actually found, and he didn't know about it, is fission. He didn't know that. So fission is, let me try and do it. Well, I'm trying to do perfect. This is what I wanted. This is what happens. This is exactly what happens inside a nuclear bomb or a nuclear reactor. So you saw what happened? I didn't, well, a proton doesn't come out, but a neutron does. So this is fission. Instead of absorbing the neutron, the uranium nucleus actually split in two. It's called fission when it splits in two. That's really what happened. Fermi didn't know it, and the team in Paris didn't know it, but in Berlin, Hahn suspected it, and Lisa Meitner was the one who proved it. But notice something happened, and that's not, it happened by chance here, but, well, that's bad, but this is okay. So when I created these two nuclei here, it basically broke apart. But what happened, oh, that's good, yeah. So I got two of these, no, they're bad. This is black now. So I've got two of these coming out, and that's the key to why the nuclear bomb, the atom bomb works and a nuclear reactor works. Nobody knew that. We're still in 1932, 33, 34, and so on. 1938, so they're working on it for years. 1938, you know what happened politically. Hitler took over Austria. And once the Anschluss, it was called the Anschluss, once the Anschluss happened, Lisa Meitner, who was in Berlin, lost her passport. She had no citizenship. She was a Jew of Austrian citizenship. At that moment, the Jews lost their citizenship, so she was in Germany without having a passport, a valid passport. And she realized she had to flee. She had to leave right away. So she got on a train in the dead of night. By that time, she was a major physicist, getting close to age 60. She has had a lot of achievements to her name. And there she is. She has to flee. In the dead of night, she gets into a train. Han gives her some diamond ring belonging to his mother in case she needs to use it to get food. And she crosses the border. She wants to cross the border into Holland. The train is stopped in front of the border. And the SS come in, and they look at passports, and they get her passport, they take it, and they leave. And she sits there for 10 minutes in terror. Then they come back, they just give her a passport, and the train continues. So she goes into Holland, but the Dutch don't want them, and I won't tell you the whole story of World War II with what happened with refugees and so on, but she had to move to Sweden. So she got to Sweden, and she got a position at an institute in Sweden, headed by a guy by the name of Sieg Bahn, who was very influential with the Nobel Committee, by the way. So, but he didn't like her at all, and she was too prominent for his taste to work in his lab, and he was kind of forced to take her. She came as a refugee. And she just hung around, and then at Christmas 1938, she went to the countryside to visit some friends in Sweden. And her nephew, who was also a physicist and kind of took after his aunt, was working in Denmark with Niels Bohr, the very famous Niels Bohr Institute in Copenhagen. So he came to meet her at Christmas in the countryside in Sweden. He took a ferry and he got there. And they're walking in the woods. She was 60 years old. It was around her birthday. He's on skis, and she's running next to him, and she's in great shape, so she continues, and they're talking about a letter that she just got from Han from Berlin. And it says, barium. I find barium in the solution. I don't understand it. Barium. Why barium? Barium is half the size of this nucleus that I just smashed. So barium's half the size. How do you send a neutron into the nucleus of uranium, and you get barium? It's not, doesn't make any sense. So they stop, and she sits on this fallen tree, and she thinks, and then she realizes what I just showed you. It broke in half, and then she derives the mathematics of it and all the energy. The energy is a very important aspect here. When you break this nucleus in half, some of the mass gets transformed into energy. Now, I can't explain it quite as well as somebody much, much more famous than me.
It followed from the special theory of relativity that mass and energy are both often different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is not equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Kokra and Walton in 1932 experimentally.
So, that was him, Albert Einstein. One of very few recordings of Einstein. You can find it on the web, but it's hard. If you Google Einstein, it doesn't come up, or at least not in the first 10 pages you look at or so. So if you want this recording for your phone answering machine or your cell phone ringtone or something like that, you have to go to AIP.org. That's the American Institute of Physics, and you'll get it right away when you get there. I think it's great. Anyway, there's Einstein explaining his formula is the only formula that every kid knows, right? E equals mc squared. I think the most famous and the only widely known formula in the world. And it's a very important formula. It says that E equals mc squared, and therefore energy and mass are the same thing. In fact, to a physicist, the difference between this and that is also energy. These are point masses, really, and they live inside here. The rest of it is really the binding energy and the kinetic energy of these guys moving around. It's very, very complicated and beyond what we want to talk about. But the quarks constantly interact through gluons. They change color and they move around all the time. Some people have a video showing some kind of a demonstration quickly, and all this motion is really the mass here. So mass and energy are the same in more ways than we even think of them. So I heard from a well-known physicist just recently, if you weigh 150 pounds, it's only 3.5 pounds that's the weight, the mass of these guys. All the rest is energy, really, this kind of motion energy. So what Einstein, that's when you wake up in the morning, you feel energetic. There's a reason for it. You are all energy with a very small amount of actual hardcore mass. So at any rate, that formula is what makes it all work, because going back to when the nucleus splits in half, undergoes fission, and about half, one goes here, one goes there, you have energy that's released. And that energy that's released can do lots of things. It can be very destructive, or it can be constructive unless you worry about nuclear waste, of course. So, yes?
Since matter is also a wave, could you explain what you mean by point mass for the inner particle?
Nobody really knows. Nobody really knows. These are called Dirac particles. They're supposed to have point mass. And I'll give you a good example. An electron is a point mass. It's an elementary particle. All physicists who deal with it will tell you it's an elementary particle. You can't break it down to something like quarks. It's like a point. I'm sorry?
But it's a wave.
It's a weight, yeah. So if you're leaning toward the direction, what you have really is the energy. Maybe that's what it is. But in terms of if you froze everything and you weighed it, so nothing is moving at all, no kinetic energy, that's what you'll get. Some mass that is sort of inherent to it. But here's the example I wanted to bring. The electron has a certain mass. Now, there's something called a muon, which is the same as an electron. It's the same point charge. It has a negative charge as well. It's the same point, but it has 207 times the mass. What does that mean? Here's a point that weighs something, the basic mass of an electron. Here's something that's the same charge and the same pointness, but it weighs 207 times more. So we don't have a perfect understanding, far from it, of what a point charge, a point mass means. But those quarks are considered elementary particles. They're points, while something else that they sit inside is really a lot of the motion energy and the binding energy holding them together. What's called the strong force that holds inside. By the way, the nucleus also is held together by the strong force. And when it breaks, it's that energy that's released when you have two pieces coming out. So Lisa Meitner understood that, and all the physicists involved in this discovery got Nobel Prizes. Of course, as you've guessed, she didn't. She had all these strikes against her. And Hahn, who at times was very kind to her, at other times less so, took over the lab once she became a refugee. And later on, when he had interviews after the war, he said, well, she just worked in my lab instead of being an equal in that, and actually the one who made the key discovery. So in 1939, I'm sorry, we're at Christmas 38. She and her nephew together make this discovery. He goes back to Denmark, to Copenhagen, and he tells Niels Bohr, look what we discovered. And Bohr is very excited. He says, this is exactly how it should be. This is it. Have you and your aunt published it yet? And he said no, and he makes some suggestion and goes on a ship that takes him to New York. So he arrives in New York in 1939. Enrico Fermi is there already. He got a Nobel Prize that year and left Europe right from Sweden without coming back to Italy. His wife was Jewish, and he was worried about Mussolini. And he was obviously strongly opposed to fascism, even though Mussolini had made him, gave him the title His Excellency, and made him a member of the Royal Academy, which Mussolini established. And there are stories about him, for example, he once came to a meeting, was chairing of the Royal Academy, and everybody was driving these great big cars with drivers. He always drove his own car, which was a small European car. And he arrived there, and he was called His Excellency, and they wouldn't let him in. And he said, well, he was thinking very quickly, and said, I'm the driver for His Excellency, Enrico Fermi. And said, okay, you can go inside and wait for your master. So Enrico Fermi still was very opposed to fascism. He emigrated to the United States, and he did it sort of sneakily. He was worried about being caught, so they had friends go into their apartment in Rome and turn on and off lights regularly, so neighbors and people walking the street would think that they're still living there, while in fact they came to New York. And so when Bohr arrived in New York with the news about fission from Europe, about the Meitner Frisch discovery, Frisch was her nephew, the two of them, Fermi, Bohr, Leo Szilard, who was an American Hungarian physicist, and John Archibald Wheeler of Princeton, the well-known physicist, met together, and they tried to analyze what goes on there, and then they made, all four of them together, this realization. Remember the neutrons that fell to the ground? One of them I cheated, but it was a proton. But one or two neutrons come out. So when it breaks, they said, well, suppose when the nucleus splits in two, you have more neutrons that come out. I mean, the nucleus is made out of protons and neutrons. It breaks into two pieces, maybe a neutron will be released. If a neutron or two are released, they in turn can hit other nuclei and cause them to break. And again, when they break in turn, other neutrons will come out and hit other nuclei. So they realized this very important step called chain reaction. So if you can create chain reaction, you can create a bomb or a nuclear reactor or other things with this kind of reaction that continues. And what happened was that the question was, is it possible? Are there neutrons that are released? Enrico Fermi started working on this problem. And around that time, scientists, once they realized, these four scientists and others, that a chain reaction is a possibility, these four scientists urged Albert Einstein, whose voice we heard, write this famous letter to FDR. And the letter said, remember, a war was going on then. The Germans may be doing this kind of experiment on uranium, and if they succeed, they will have a doomsday weapon. We have to do something to counter it, or Hitler will rule the world. Now, FDR listened to him, and the Manhattan Project was launched. And in fact, Einstein and the other scientists were right. In 1972, I was a physics and math student at Berkeley, and we had a visitor named Werner Heisenberg. So I got to meet him, and he was very charming. He was 70 or 71 years old, and he walked very tall, and he had this glint in his eye, and he was this German golden boy. And the audience was about 3 times the number of people here, all the physicists and mathematicians and some other people, and everybody came, and he gave a brilliant talk about quantum mechanics. He derived matrix mechanics. So the first approach to quantum mechanics, they use this matrices, and if you're interested in that, matrix multiplication, as some of you may know, is non-commutative. Matrix A times B is not the same as B times A in general. So there's some cases where it is. In quantum mechanics, there's the same thing. If you do something and then something else, it's not the same as if you do the something else first and then the something. Why? Because of Heisenberg. Heisenberg also is famous for the uncertainty principle, right? So if you measure, say, suppose I have these particles. I guess I could use them. So let's take, no, the electron's better, but anyway, let's suppose I'm measuring this proton. It's moving here. And if I measure it and I find where it is, then I don't know its speed, its momentum with precision, because, that's how the quantum world works. There are good proofs of it using the Heisenberg microscope, if you're into that. At any rate, and if I measure how fast it's moving, I don't know its position with precision. And that's not something that's in us, in how we measure things. It's really a property of the quantum world. That's just how the quantum world is. It's very, very bizarre. And people will tell you, if you understand the quantum, you can't believe it. And if you believe it, you can't really understand it. There's the uncertainty about it. So there are physicists who spend their entire lives trying to understand how the quantum world works. And it's so unintuitive to us because everything in our existence is non-quantum. We have cause and effect. If I smash this against the wall, I know what will happen. It's not the same in the quantum world. So he gave this brilliant talk about quantum mechanics, and nobody in the audience asked him, "Excuse me, Professor Heisenberg, what did you do during the war?" So I'll tell you what he did during the war. 30 years later, so this was 1972 when I met him and I heard him speak. 30 years later, in 2002, I was in New York, and I got to see that play, Copenhagen. And the play by Michael Frayn, very brilliant play. Have you seen it, any of you? So it has three actors, right? There's Bohr, there's his protege. He's not a student because he already had his PhD when he came to Denmark to work with him, but he was his mentor. He was older and he was his mentor. And Bohr's wife, Margrethe Bohr. And the three of them talk. I think they're dead, and they talk about what happened before. Are they dead? Or their spirits? Or they're talking what happened in 1941. When Heisenberg came to see Bohr. He remained in Germany. And by the way, Heisenberg came to the United States in 1939. And everybody, all the scientists had already left, all the well-known scientists had left Germany because, they lost their jobs because of Hitler. So they came here, mostly Jews, but others too. So they all said, please, find a position here. Go to any university. Any university will take you. You're a world-famous scientist. And he said, no. He returned to Germany. He said, I'm German. I'm staying in Germany. So he remained in Germany. And Hitler, of course, got him pretty quickly. He was a top physicist. And the work of Hahn in Berlin also was known to the Nazis. And the Nazis actually called them up and said, we want to establish this program to make an atom bomb. So now the Germans, even the few who remained there, headed by Heisenberg, and there were several others there, such as von Weizsäcker, whose father was actually a real Nazi, and he was a scientist who worked with Heisenberg. So at any rate, they started this program, and in 1941, and nobody knows the exact date, it was in the fall of 1941. Some people, Heisenberg doesn't remember when it happened, and Bohr didn't remember either. One of them said it was in September, one said it was in October. He comes on a train to Copenhagen to meet Bohr, his old mentor. And the meeting is very strange from the beginning because Copenhagen, all of Denmark is occupied territory, occupied by Germany. And the SS sort of follows him around, and everywhere they go, they're followed and they're listened to. So they meet, and the play looked at different possibilities. And one of them that I remember well was Heisenberg supposedly coming to Denmark to talk to Bohr about the scientists getting together and across the two sides of the war, and convincing their governments not to pursue nuclear weapons and to do things for peace and so on. That's not what happened. None of these 3 or 4 possibilities of the play ever happened. What happened was something else. Now, it's a matter of opinion. I became convinced that none of these scenarios are true and that there's another scenario that is the real one. So after the play came out, there was a lot of huge public interest in what happened in 1941, and the Bohr archive was forced to release documents that had to remain, they were supposed to remain sealed until 2012, according to Bohr's will. But because there was so much of an outcry, they were forced to release these documents to the press, to make them available to people in 2002. And these documents show a different possibility altogether. And they are the letters that Bohr wrote Heisenberg in 1957. In 1956, a book by Jungt appeared in Germany that showed Heisenberg in very positive colors. You know, he was this great scientist, and he didn't try to create a bomb. He built a reactor under a church in Germany, under a church in the town of Haigerloch. And there's a cave there, and he built a reactor, and had he worked long enough, he would have produced enough plutonium to make a bomb. He was smart enough to know that. So it wasn't just working with little radiation. You know, he knew exactly what he was doing. At the same time, in other places in Germany, there are other centers for research that were somewhat similar to the Manhattan Project in this country. They knew 3 ways of refining uranium. It shows you the Germans in wartime were doing all that. We did the Manhattan Project pretty quickly. The Iranians are now working on trying to make a bomb for 20 years. So hopefully we'll stop them. So at any rate, they understood that there are 2 ways to make a bomb. And these are all transcripts that you can see. They knew that you can make a bomb from plutonium, which is the transuranic element, but it's produced in a different way. It's produced in a nuclear reactor. And plutonium will make you a bomb, the same as uranium-235. Uranium-235 is the rare element, 0.7% of all the uranium in nature is 235. That's the one that will produce abundant neutrons and will work well. Uranium-238 is more inert. It can work in a reactor when it's slightly enriched. But if it's highly enriched, it's 85% or higher. Uranium-235 will allow you to make a bomb. So when the Iranians say, we are doing this for power, that's nonsense. That's like the energy that they use to refine this uranium is wasted. And if they use then the uranium-235 in the reactor, it's overkill that is unimaginable. Because uranium-238 will work just fine. So when they refine uranium to get a high percentage of 235, that's only for a bomb. So this is really a hypocrisy, but this is an aside. So at any rate, they knew there are 2 ways, uranium-235. They knew 3 ways of refining uranium-235 and 238. They knew they could make it from plutonium, even though the name wasn't known, wasn't coined. And what then prevented them from getting a bomb? Hitler. Hitler prevented Nazi Germany from getting an atom bomb. See, Hitler gave funding, very liberal funding, to the nuclear bomb project headed by Heisenberg in Haigerloch and other people in other places. And they were making progress. And then Hitler changed his mind. In the middle of the war, he diverted all the funding from the nuclear bomb project to Peenemünde. You know about Peenemünde. That's where the V1 and V2 rockets were made. So all that funding went there, and these rockets were very effective. They rained terror on Britain. But at least the Nazis didn't get a bomb. Now, some people say that also the Allies bombed the heavy water installations, and you may have seen there's a great movie about it in Norway. And that's true. That's part of the reason they were prevented. But also funding was a major project. So it was a major problem. So at any rate, Enrico Fermi did the same kind of an experiment as Heisenberg did in Germany under the football field at the University of Chicago. It's called the Chicago Pile 1. And he proved experimentally that what I showed you here does work. You have neutrons that come out. And he actually created this reaction. Now, it would have gone like exponentially in terms of the explosions, but he stopped it right at the right point by raising rods, like they do in nuclear reactors, slightly, a millimeter every few minutes, and measuring the radiation, measuring the flux of neutrons that occur there, that are produced. And he knew exactly when to stop it. Then he said, OK, we got it. Everybody clapped. Big success. And from there, the road was open to Manhattan Project and the making of the American bomb. Now, am I supposed to stop around now? Or I'm sorry.
Entirely up to you.
Oh, well, I'll tell you what. So we are at the Manhattan Project. The bomb is made, and there are 2 kinds of bombs that are made in the United States. And the Manhattan Project was all over the country. There's in Hanford, in Washington, in Tennessee. There was a center at various universities, and it was headed, of course, in Los Alamos, in New Mexico. On the 16th of July, 1945, a bomb was tested, the Trinity test, at the Trinity site in New Mexico. And this was a plutonium bomb, which worked by implosion. You have a certain amount of plutonium in usual conventional explosives around it, when they blow up, they force it to get more condensed, and then the matter there can achieve that chain reaction because the atoms are closer. And the uranium bomb is different. It's a different design. There are two pieces of uranium-235, mostly 235. One, say, sitting here, and the other one sitting here. And the two pieces are subcritical, meaning the flux of neutrons is not enough to explode. Otherwise, it would be too early. So, and there's a charge here, a conventional charge, and when it explodes, it sends one piece into the other. So it's like a gun type of design. And then you have two pieces together whose total mass is enough to go critical, and the bomb explodes. And that's what happened in Hiroshima. The first uranium bomb exploded was Hiroshima. Nagasaki was, again, a plutonium bomb. Most of the bombs that existed there are plutonium bombs because it's easier. You have a nuclear reactor running for a while and it produces plutonium. So it's cheaper to do that than to refine uranium. So why the Iranians use uranium, who knows? That's just a decision they've made. At any rate, this is what happens. And later on, after the war, Teller designed something for a we're talking about fission bombs, right? Bombs that are, the energy is from breaking of nuclei of uranium. But if you go one step higher, you can fuse nuclei of hydrogen, and then there's more energy that comes out. So if you use an atom bomb, like the bomb that destroyed Hiroshima or the Trinity site bomb, and you put some element there that holds a lot of hydrogen sort of condensed together. They use a metal to bind it. When that happens, the heat from the fission bomb creates the fusion. So it blows your mind. I mean, 15 kilotons destroyed the city. What more do you want? But when you think back to the Cold War, I think they're all insane. Bigger and bigger and bigger bombs. And I think the biggest bomb was about 50 megatons, was a Russian bomb, about 50 megaton. But I think that there might have been some bombs that were larger than that even. But the most well-known, and you could look it up, is a 50 megaton bomb. So Hiroshima is roughly 15, plus or minus 5, 15 kilotons. So if you go megaton is, 1,000 times more. So I mean, you can destroy a city with much less. Why do you keep going for bigger and bigger bombs? So after the war, there was this race with the Soviets called the Cold War. Some of you still remember it. And the Cold War, that's what they did. They built bigger and bigger and more bombs until they reached a point where they could destroy the world many, many times over. But that wasn't enough. So in the 80s, there was some kind of research that led to a conclusion called nuclear winter. Does anybody remember that? Nuclear winter hypothesis is that if enough cities are burned with nuclear explosions, the soot that goes up in the atmosphere causes the opposite of what we're supposedly having now, the global warming. There will be global freezing because the light from the sun can't penetrate through this stuff that's in the atmosphere from the burning cities. And that will cause the whole planet to die because we'll freeze to death. And then people start saying, oh, no, atom bombs don't work. And that was part of the reason why the Cold War ended, when that realization. Now today they're saying that even a limited war, such as something in the Middle East, with 50 atom bombs is enough to cause nuclear winter. So nuclear bombs are really bad, and I think I'll stop here. If you have any questions, I'd love to try and answer them. Yeah.
Elaborate on what I think is called a neutron bomb?
Yes, good question, yeah. A neutron bomb is something very small. It's about a kiloton. So it's these are the big bombs are strategic bombs. They are destroying cities and large things like Air Force bases and things like that. A neutron bomb is something small that can sit in a howitzer cannon inside a large shell for artillery. And that makes a small explosion. If you think of Hiroshima as 15 kilotons, this is 1 kiloton. So it's roughly 1 kiloton. So it's about a 15th of a city being destroyed. So that's enough to destroy a block, I guess. Now, there's something else about a neutron bomb. The neutron bomb is called the capitalist bomb, is what it's dubbed the capitalist bomb. Because what happens with a neutron bomb is that the reaction is not completed. What you get is the flux of neutron without the thermonuclear, without the huge explosion. It's just a huge flux of neutrons that happen from this chain reaction. But it's tinkered with in such a way that it doesn't achieve the full blast, but rather this neutron. So if I exploded, God forbid, a neutron bomb right here, we'll be pierced by neutrons, but the walls won't break down. Well, in a room maybe, but I mean, out there, buildings won't be destroyed. That's why it's called the capitalist bomb. The buildings stay, but the people die. And in a limited range, that's a neutron bomb.
And are shelters that are used to prevent radiation exposure useful for neutron bombs?
That's a good question. I'm just reading now a book about Hiroshima that is still in manuscript form by somebody else, and it will be published in a few months. And it has a story that I didn't know, that some people working in the bank vault in Hiroshima survived. So a bank vault, lots of, protection, and they were within the 1 mile center. So they did survive. So, well, you can do a calculation if you're a physicist in terms of what. Well, we all know that lead protects us from radiation. The reason lead protects us from radiation, by the way, uranium will eventually become lead when radium and radon gas and all these things come out, and the thorium and so on. Eventually, if you have a piece of uranium here that's allowed to disintegrate completely, and there's several processes by which it can decay, will eventually become lead. So, and lead is, like uranium, is very, very dense. So the reason it protects us is it's extremely dense. You have lots of these guys here, so that any radioactive thing, like a ray or a particle, an alpha ray or a beta ray, is likely to be stopped when you have a high density of these things here, these little balls. So lead is very, very dense, and therefore gold will work too, and silver and steel would work too. But the best is apparently lead, and therefore, if you think of lead, lead will protect you, and will a fallout shelter protect you from a neutron bomb? Well, it depends.
Something about the neutrons will go through walls and steel structures.
Right.
I didn't hear it clearly, and so it gave
Yeah.
me the impression that it might pierce shielding that would.
Yeah, it depends. It depends on how thick the walls are.
A little confusion here on that one.
Wait, I'm sorry, hold on one second. We need to get the mic, because otherwise the conversation doesn't get.
Look, yeah. Let me explain what I was trying to say before. If you have a blast out there, okay, the blast, the blast itself will make the buildings fall, okay. Many of the buildings here, because well, it's a blast. You have this shock wave. The neutrons are not, if the neutrons penetrate this building, it doesn't do anything to the building. But if you sit inside the building and you're not protected by, say, 10 feet of lead or something, the neutrons hitting you will eventually kill you.
I understand that a number of the scientists who worked at Los Alamos had serious misgivings, even as they were working on developing the atomic bomb, on what they were doing and so on. And I was wondering, is that true? And maybe if you could speak to that, both I guess, during the war and after the war, what the scientists
Yes.
thought. Yeah.
Yes, it's very, very true. In fact, in preparing this book, I spent several weeks at the American Institute of Physics in Maryland, and I read all the transcripts of scientists who took part in the Manhattan Project. And many of them expressed regret afterwards, but many, actually, some of them at least, expressed serious concern at the time. Now, let me explain why, and that comes through with every transcript. Some people said, well, the Japanese were cruel to us, Pearl Harbor and so on, and I didn't really feel any sorry for them at all. Others had much more serious concerns, and that happened also in real time. Let me explain why. Remember, many of these scientists were Jews escaping Germany, and therefore had felt on their flesh what was happening in Germany. Their own families were exterminated in Auschwitz and elsewhere, and they knew what was going on. At least some of them knew some of the horror that was going on. So they really were concerned with stopping Hitler. That's why they gave their time and expertise to the Manhattan Project. But the war in Germany, in Europe, ended in May 1945. So there's from May till August 1945, The bomb was ready in July, and in August it was dropped. August 6th it was dropped on Hiroshima. Leo Szilard, who was a scientist I mentioned earlier, the Hungarian American scientist, was extremely concerned about this, and he was in many ways the conscience of a large group of scientists, 68 of whom signed a petition headed by him, which was to be sent to FDR before he died, asking him not to use the bomb on people, but rather to do a demonstration. And that becomes clear from all these transcripts that I've read and also things that are publicly available. The Szilard petition is very well known, and it basically asked the president to, if the bomb is used, to use it on a desert island in the Pacific or on a battleship. It was one of the proposals. Or in another way, to show the Japanese that we own we possess this weapon, and why, then if they don't surrender, you can use it on the city. And there are certainly, one of the arguments, we had only 2 bombs, and one that was exploded at the Trinity site, but the process was going, and 2 bombs is enough, I think, anyway, but the production was going in such a rate that within a few months there would have been 10 bombs and so on. So the Szilard petition never made the FDR. FDR died in the middle of the war, as we know, and Truman took office, and the Szilard petition went to a person who was about to become Secretary of Defense under Truman, but he didn't have any power at that time. It didn't go any further. There are lots of details about why this happened. The Szilard petition, we're not sure whether the Szilard petition ever made it to Truman, but there were other moves, and many other scientists expressed expressed themselves in other ways, and showing their objection to using the bomb that they helped create on people. If you would ask me what percentage, I would say about half the transcripts I read expressed, the people who were interviewed expressed regret and or a prior objection to using the bomb on people, and about half, or a little less than half, showed no remorse at all. So I hope I answered your question. Good.
And we have time for one last question.
Okay.
Yes. In the book, in your book, we read about the glow in the laboratory.
Right.
How did they make the leap that you could see inside the body with X-ray? I didn't quite follow that.
That's a good question. I think there was a lot of experimentation. And in fact, if you go online, you can see Röntgen's wife's hand. So one of the first X-rays was her hand. I think it was experimentation to see. He figured out that something was going from here, there, and would that something go through something in between? So there's experimentation well, here's the glow is here, and the source is here. You try and block it, and if the glow continues, then that tells him that it goes through, that the rays go through. And so he experimented with himself, with his wife, and actually Marie Curie's daughter, Irene, operated the first X-ray machine. So this is a few years later, about, a quarter century later, a little less, 20 years later, during the First World War. In the field, they were using some X-ray machines to see whether there were broken bones with soldiers that were wounded. So these were the first X-rays. So it was experimentation.
Well, thank you very much, Professor Aczel, for that lovely program. Professor Aczel will be available to sign books if you would like to have your copy signed, or if you would like to purchase a copy, we have some for sale over here. Thank you very much.